We're taking another deep dive into the math map, and this time we're looking at this idea of accumulated change. It touches on some concepts that feel like they should be complicated, but the more you dig into them, they're actually things we experience every day. And so today we're going to try to break some of this down, especially as homeschool parents might be thinking about, how do I even begin to introduce this to my 7th grader?
And we're pulling specifically from Scholars and Socials today.
Yes.
Which is such a great resource because it's created by homeschool parents.
They just get it. And they're speaking the language,
Yeah.
and they're really trying to make these things accessible. Our mission today is to really demystify some of these terms like rate of change, even derivatives, and show you how they're not just abstract math concepts living in a textbook, the things that describe the world around us.
Yeah.
And the goal is to really build this solid foundational understanding without diving into super complicated calculations or formulas.
Yeah, no big equations today.
We're just trying to get to the core idea and feel good about that. So to kick things off, maybe let's just start with the basics. What exactly do we mean by rate of change?
I think the best way to understand this is with an example that we can all relate to, a family road trip.
Okay, I love a good road trip analogy.
Right. So let's say you're driving 200 miles and it takes you 4 hours to get there.
Okay.
What would you say your speed was for that trip?
The simple answer is 50 miles per hour.
And that right there is your average rate of change.
Ah.
Your average speed over the entire trip. It tells you how much your distance changed over a certain period of time.
So it's the total distance divided by the total time. Okay, I see.
That gives you an overall sense of how quickly or slowly your position was changing throughout the journey.
Makes sense. I'm seeing here in our source material, it says that calculus allows us to zoom in on change. How does that play into our road trip example?
Think about it. While your average speed was 50 miles per hour, your actual speed probably varied throughout the trip.
Of course.
You probably sped up on the open highway, maybe slowed down going through towns, maybe even stopped for a bathroom break or to grab some snacks.
Yeah, definitely guilty of that.
So while the average gives you a general idea, the reality is that your speed was constantly changing.
So how does calculus help us see those moment-by-moment changes?
This is where the concept of a derivative comes in. You can think of a derivative as a tool that lets us pinpoint your speed at any exact instant during that 4-hour drive.
What my speedometer would show at any given moment.
Exactly. It's like taking a snapshot of your speed at a precise point in time.
Okay, while the average is 50, the derivative could tell us at, say, 2:17 p.m., the car was going 58 miles per hour. That's cool.
It's like a mathematical microscope focused on a single point in time.
I like that. That makes it so much less abstract.
And understanding this instantaneous speed, it's not just about knowing how fast you were going at one point.
Right.
It's a fundamental idea that can help us predict where things might be headed in the future.
Oh, interesting.
Whether it's the path of your car or the growth of the population, the instantaneous rate of change gives us valuable information about the dynamics of the system.
It's not just looking back. It's also looking forward, which makes sense. You're thinking about rates of change. You're thinking about where things are going.
And it's all around us, too. Think about the speedometer in your car.
Yeah.
It's constantly changing, showing you your instantaneous speed at that very moment.
It really is instantaneous dense, right? It's happening right now.
The derivative is the mathematical way to represent what your speedometer is doing.
I love it. Okay, so we've talked about a car moving more. What about other examples? I know the source material also talks about a ladder sliding down a wall.
Yes, that's a classic example to illustrate how rates of change can be connected.
Okay, how does that one work?
So picture this. You have a ladder leaning against a wall. And for whatever reason, the top starts to slide down. As the top slides down, what happens to the bottom of the ladder?
It has to move outwards, right?
Exactly. And here's the thing. The rate at which the top is sliding down is directly related to the rate at which the bottom is moving out.
Interesting. They're linked. Yeah.
And calculus, specifically a concept called related rates, lets us figure out exactly how those two rates of change influence each other.
So it's not just about individual things changing, but also how those changes are intertwined.
And that's where things can get really interesting and powerful in terms of understanding complex systems.
So I'm looking at the source material here, and there's a whole table of derivatives and different rules, like the constant rule and the power rule.
I can definitely see how it could be overwhelming, especially if you're not super familiar with calculus.
Yeah, and I'm not sure my 7th grader is ready for all of this.
And that's perfectly fine. For what we're trying to do today, which is build that foundational understanding, we don't need to dive into all the specific calculations and rules.
So those rules are more like shortcuts or tools for when you want to calculate things precisely.
But for now, let's not get bogged down in the how-to and focus on the what does rate of change actually mean? And just like with anything else, you can appreciate a beautiful piece of music without understanding all the technicalities of music theory.
That's a great analogy. I love that. All right, so we've been talking about this abstractly, but is there a way we can visualize this idea of instantaneous rate of change?
There is definitely, and it involves our good friend the graph. So imagine a curve drawn on a graph, any curve. Now picture taking a straight line and just barely touching that curve at a single point. We call that a tangent line.
All right, so the curve is like a winding road, and the tangent is like a little straight section of that road.
And the slope of that tangent line represents the instantaneous rate of change at that precise point on the curve.
So a steep tangent line means things are changing quickly at that moment.
Think of a skateboarder on a ramp. If they're on a steep part, their speed is changing rapidly, and the tangent line to the ramp's curve would be very steep.
So the steeper the line, the faster the rate of change.
Exactly. It's a visual way to represent how quickly or slowly things are changing.
I'm starting to see how this all connects now, but
Yeah.
I can still see how the difference between average rate of change and instantaneous rate of change might be a little confusing. Can we hit that one more time with another example?
Sure, let's go back to the kitchen this time. Let's say you're baking cookies,
Okay.
and you manage to bake 24 cookies in 30 minutes.
Delicious.
So your average rate of cookie production is 0.8 cookies per minute. But think about the actual process of baking those cookies. You're not placing them on the baking sheet at a perfectly constant rate.
No way, there are definitely moments of flurry and then pauses.
Exactly. There are times when you might place several cookies in quick succession, and then times when you pause to get more dough or rearrange the cookies on the sheet.
So the instantaneous rate of change would be like capturing the speed at which you're placing those cookies at any given second.
Exactly. It could be super fast during those bursts of cookie placement, and then 0 when you pause.
That makes so much sense. It's like those little moments within the overall time frame.
And the derivative would allow us to pinpoint those moments and see how the rate is fluctuating.
Wow. Okay. So we've talked about cars, ladders, cookies, all kinds of things changing. But does this idea of derivatives actually have real-world applications that my seventh grader might relate to?
Absolutely. There are tons of examples even beyond what we've already discussed.
Okay. What?
Think about the growth of a plant.
Yeah.
You might measure its average growth over a week. Let's say it grows 2 centimeters per week.
Yeah.
But the rate at which it grows likely isn't constant. It might grow faster during a sunny period and slower on a cloudy day. The instantaneous rate of change, the derivative, could tell us exactly how fast it's growing at a specific moment.
Oh, wow. So it's not just about the overall growth, but those tiny changes from moment to moment.
And those tiny changes can give us valuable insights into how the plant is responding to its environment.
That's fascinating. What about other examples?
What about a ball thrown in the air?
Okay. Yeah.
Its speed is constantly changing due to gravity. A derivative can help us determine its exact speed and direction at any instant during its flight.
Oh, cool. So if you're trying to calculate where it's going to land or something.
Exactly. The movement of planets in their orbits also involves constantly changing speeds, and derivatives are essential for astronomers to understand and predict those movements.
Wow. So it really is everywhere. It's like this hidden language that describes how things change.
It is. And once you start to see it, you'll realize just how fundamental this concept is to so many aspects of our world.
Okay. So the source material goes on to introduce these basic differentiation rules, like the constant rule and the power rule. Do we need to get into the nitty-gritty of those with our seventh graders?
I wouldn't say it's necessary to delve into the specifics of the calculations at this stage. The key thing to understand is that mathematicians have developed these rules as efficient shortcuts to find derivatives.
So instead of having to go back to the basic definition, every time we can use these rules to quickly find the answers.
Think of it like this. You could walk to the grocery store, which would take a while.
Yeah.
Or you could drive, which is much faster. The rules are like having a car. They get you to your destination more quickly.
Okay, so what's the constant rule all about?
The constant rule is pretty straightforward. It basically says that the rate of change of a constant value is always 0.
Meaning if something isn't changing, its rate of change is 0?
Think of a horizontal line on a graph. It's not going up or down. It's perfectly flat. So its steepness, its rate of change is 0.
Makes sense. No change equals a rate of 0. What about the power rule?
The power rule is a bit more involved, but it's a shortcut for finding the derivative of variables raised to a power like x squared or x cubed.
So it helps us deal with those exponents.
Right. Again, we don't need to dive into the specifics of how it works, but it's good to know that such a rule exists and that it helps us understand how these types of functions change.
So it's like another tool in our toolbox.
And as your student progresses in their math journey, they'll learn more about these rules and how to use them effectively.
Awesome. The briefing also mentioned something about using the first and second derivatives to analyze how a function behaves. That sounds pretty advanced. What's the basic idea there?
It is a bit more advanced, but we can definitely touch on the main points. The first derivative, as we've discussed, tells us whether a function is increasing or decreasing at a specific point.
A roller coaster example going uphill means the function is increasing, going downhill means it's decreasing.
The second derivative gives us information about the shape of the curve, how that rate of change itself is changing.
It's like the rate of change of the rate of change.
It tells us if the function is curving upwards like a smile or curving downwards like a frown.
Interesting. So the first derivative is about direction, and the second derivative is about shape.
In a nutshell, yes. And these are just different lenses through which we can understand the behavior of a function and gain insights into the real-world phenomena it might represent.
That roller coaster analogy is really helping me grasp this.
All right, one last thing. I saw the briefing mentions differentiability. What on earth does that mean?
In simple terms, a function is differentiable at a particular point if its derivative exists at that point. Visually, this means you can draw a nice, smooth tangent line at that point on the curve. Think about drawing on the curve with a pencil. If you hit a sharp corner, you can't really say there's one single direction the curve is going in at that point. That's why we can't draw a single, clear tangent line, and the function isn't smooth enough or differentiable there.
So differentiable basically means it's smooth enough that we can find that instantaneous rate of change. Why is that important? Because if a function is differentiable, it means we can use all the powerful tools of calculus, like finding its derivative, to analyze its behavior and gain deeper insights. It's like having the right key to unlock a more complete understanding of that function and the real-world phenomena it might represent.
That makes sense. Wow, so we've covered a lot.
We have.
To wrap things up, I wanted to touch on a really interesting question that the source material brings up. It asks, does God use a heavenly calculus to see the individual changes in our lives with mathematical precision? What are your thoughts on that?
It's a really profound question, and one that encourages us to think about the nature of change and growth, not just in math, but in our own lives.
It does, and it connects to the idea that growth and change in life, whether it's personal growth, learning a new skill, or even just the natural processes of life, isn't always a straight, predictable line. There are times of rapid progress, like when you're first learning something new, and then there are times when change feels almost imperceptible.
Much like the varying rates of change we see in math functions, there are steep inclines of rapid growth, like a roller coaster shooting upwards, and then flyer sections where change seems much slower.
And it's interesting because even during those plateaus where it might feel like nothing's happening, there could still be subtle shifts occurring. Just like a derivative can still provide information, even when a function appears relatively flat at a specific moment.
That's such an encouraging perspective. It's a reminder that progress isn't always linear or obvious. Those ups and downs, those periods of rapid growth, and those times of seemingly slower change are all part of the journey.
Absolutely. It's a natural part of how things unfold. And in its own way, math provides a framework for understanding and even appreciating that reality. So as we think about our listeners approaching this topic with their seventh graders, what would you say is the most important thing to keep in mind?
I'd say the key takeaway is this. Rate of change is simply about how things are changing. And the derivative is this incredible tool that lets us zoom in and understand that change at any specific instant. The focus, especially for this stage, should be on grasping that core concept through relatable, everyday examples. Sparking curiosity and encouraging those aha moments is far more valuable than memorizing formulas or diving into complex calculations right now.
I love that. It's about making these abstract ideas feel concrete and accessible for both the parents and the students. And who knows, exploring these concepts together might even spark some really interesting dinner table conversations about the world around us.
It very well could.
I feel much more confident about tackling this week's material. Thank you so much for breaking this down with us.
My pleasure.
And thank you, dear listener, for joining us on this deep dive.
This is